Phospholipids are another type of lipid produced from fatty acids. Recall that triacylglycerols were created when a glycerol molecule linked three fatty acids through ester bonds. A phospholipid, by comparison, has a glycerol backbone, but only two fatty acids link with it to form tails. In the third position, instead we have a phosphate group that links to something called an amino alcohol, which we'll discuss in a moment. Another type of phospholipid is called a sphingomyelin. And a sphingomyelin, or myelin, consists not of a glycerol backbone, but of a backbone with a molecule called sphingosine, which links to one fatty acid, a phosphate group, and the phosphate group also holds on to an amino alcohol. Sphingomyelins are found primarily in the nervous system. Phospholipids, like the glycerophospholipid on the left or sphingomyelin on the right, contain an amino alcohol, which is a new compound we haven't discussed before. An amino alcohol is one of the three compounds shown along the bottom: choline, serine, or ethanolamine. Notice these compounds all have two things in common. One, they have an alcohol functional group, and that alcohol functional group is what bonds to the phosphate in the phospholipid. At the other end of each amino alcohol, there's some functional group that bears a net charge. As we'll see, it's this charge that makes phospholipids different from things like triacylglycerols. Here are some full structures of phospholipids. Each part of each of these structures is color-coded to match the color-coded cartoons from the previous two slides. The phospholipid on the left has the glycerol backbone that links two fatty acids. And notice the ester bonds that are linking the fatty acid tails. A phosphate group in the third position links the glycerol to the amino alcohol, here choline. On the right, we have a similar phospholipid. Again, our glycerol backbone with two fatty acid tails linked by ester bonds, and in the third position, a phosphate group that connects to another amino alcohol, here ethanolamine. Of course, it's important to remember that charged functional groups and greasy hydrocarbon tails don't really get along. And the real structure of a phospholipid probably looks more like what you see on the screen now. Here, the greasy hydrophobic tails are repelled away from the hydrophilic ionically charged head of the glycerophospholipid. The cartoon along the bottom diagrams this and shows that phospholipids typically have a polar or hydrophobic head and these nonpolar tails, which leads to many of their properties. When phospholipids form membranes in cells, the polar head is attracted to water and the tails stay buried, forming the membrane layer. Sphingomyelin, or myelin, is another type of lipid that includes a phosphate group, as we've seen before. The difference with sphingomyelins is that a new molecule, not glycerol, forms the backbone. Here, the molecule sphingosine forms the backbone. There's only room for one fatty acid tail, but we still have our phosphate group linking to an amino alcohol. Here's the structure of a sphingomyelin. Again, it's not glycerol as the backbone, but a different type of molecule. However, it serves the same purpose. The sphingosphene backbone here can link to a fatty acid, hold on to a phosphate, and link to an amino alcohol. Sphingomyelins are found primarily in the nervous system, and they form the primary component of myelin, which is the insulation that's around each nerve cell. Nerve cells conduct electrical impulses, just like the wires in your home or an electronic device, and they require this coating to keep the wires insulated of the nerve cell. In some neurodegenerative diseases, like multiple sclerosis, myelin is damaged so that the nerves can't transmit the electronic impulses properly.